We have already discussed the most important resampling technique that is used, bootstrapping. Now we shall start discussing the next most important resampling technique, which is called cross-validation. Cross-validation is a lot less sophisticated than bootstrapping. It can be explained quite easily. It is a lot less ambitious also, but very useful for certain special types of applications. Now, the technique is quite simple. It follows the same general setup as in any sampling technique. So we have this thing, we have got past data, we have got some statistical method, and we have drawn some inference. We want to validate it, we need future data, and based on that only we can say whether the method is good or bad. So that is the general setup of any resampling technique. So you have got some past data. That's your past data. Now we are going to use this as a proxy for future data using some clever thing. The clever thing in case of Bootstrap was first you estimate the empirical distribution function, then you simulate from that, or you use residual bootstrap, etc., etc. There are theorems, so Grebenko-Cantelli theorem to justify those steps. But in case of cross-validation, it is far easier. What you do is you just split it up into two parts. Here's the entire past data set. You split it up into two parts, the blue part and the red part, as I have shown. One part typically larger than the other. And then you just say that, well, I really do not have the red part. I have only the blue part. Use only the blue part as your past data and keep the red part as a proxy for your future data. That's it. So the red part is not at all used as an input to your statistical method. It is used only for the validation. This is called the training part and this is called the test part. That is the terminology used in the world of cross-validation. Now again, if we use the analogy of student and teacher, we can think of this in the following way. The thing that I showed just now, that was basically all the problems that the teacher had in mind. So he had all these problems which are sort of worked out problems, and he split this up into two parts. The blue part are the things that the teacher used to teach in class. So presented all those things as worked out examples and left all the remaining 10 as reserve, and he asked them in the exam. So the training part are the worked out examples that the teacher used in class, and the red part is the test set which is used for the test, the exam. It's a very simple idea. The only thing is that you might object, how do I really choose that test part? In this diagram it seems that I take just the bottom few rows as my test part. No, that would not be a good idea. It's a good idea if you pick them randomly. So you can pick a random fraction of the entire thing. So what people typically do is this, that they will split the entire data into say 5 parts, equal parts, more or less equal parts if the number of cases is not divisible by 5, and then pick one part at a time as your test set and the remaining as the training set. So you loop over all the parts. This thing will become clear once we see the R implementation. And then you apply your technique and find a performance coefficient, which is typically called the cross-validation score. For each one of the choices of the test set, you average over them and you get a number. That measures how good that particular statistical method is. Sometimes people choose only one case as your test case and the remaining thing as your test. So that is called leave one out cross-validation, because at every step you are leaving one out. So first you leave out the very first case, work with case number 2 to end. Then you return that case 1 back to the pool, remove only case 2 and you work with case 1, 3 all the way up to end. And you do it like this and finally average. This is not a very nice way of doing things, because testing on something of sample size 1 is not a good idea, so most people will go for something like 5-fold cross-validation or 10-fold cross-validation. These are by all means the most popular variants of cross-validation. Now, before we start working with R, implementing cross-validation in R, it is important to know where cross-validation is typically used. We have seen that bootstrapping is typically used where we are interested in the sampling distribution or quantities related with the sampling distribution of various statistics. So we do not know the underlying distribution. We have a statistic. We want to know something about the sampling distribution. Then we use bootstrap. That is the main application of bootstrap. It may be used for other purposes also, but that is the main thing. Similarly, cross-validation also has its main thrust area. In fact, it has got two different thrust areas. The first one is where you have some kind of a machine learning problem. So, in the statistical parlance, we should call it a pattern recognition problem, not a machine learning problem. So, the idea is this, that you have certain features about certain individuals given to you, and you want to identify that particular individual. A very simple example would be where you have, say, you want to recognize a particular printed character or maybe handwritten character, and you have made certain measurements from the image of that character, and based on that you want to say this is A, that is B, like that. So when someone now gives you a new image, you want to say that yes, this one is A, that one is B. So whenever you have any such problem, cross-validation is very helpful. The idea is here are certain images. For each one of them, you are given the true identity of those images. This is A, this is B, this is C, etc. You take part of them as worked out examples. So you fit them into your pattern recognition algorithm, and it learns some way by which it can say, based on the image, that this is this and this is that. Now, you look at the test part of the data and you give your algorithm those things without telling it the true identity, and you can check whether your algorithm is identifying them correctly or not. You can check that because you know their true identity and you are seeing what your algorithm recognizes it as. So if it is really A and your algorithm says B, you know that there is a mismatch. If it is A and the algorithm says it is A, then it is correct, like that. So that is why cross-validation is very popular in the pattern recognition or machine learning world. Whenever you have a method, you have two different methods that you want to compare. Well, apply cross-validation to both of them and see which one performs better. Now the other application which is very useful. Now the other application which is also very useful is a more statistical one. It is about choosing the value of some tuning parameter. In many cases, you have some particular technique in mind, possibly based on heuristics, etc., where there are certain things that you cannot work out by heuristics. Like, for example, you have some situation and you understand that you must use a threshold. If something is above a threshold, you should do something. If it is below a threshold, you should do something else. That is clear, that you need a threshold. But what is not clear is what should that value of threshold be. Then the threshold value is a tuning parameter. This is not a parameter in the sense of a model parameter. This is just a technique or a family of techniques. For different values of the threshold, you get different members of the family, and you are trying to pick that particular technique which suits you the best. As yet another example, it could be like this. You are trying to fit a polynomial to some data, and there is no domain knowledge which prescribes what particular degree of polynomial you should fit. In that case, the degree of the polynomial, that is a tuning parameter. Once you know the degree, then it becomes a linear model problem and you can use your standard software, but you do not know what degree you should go for. That degree will be a tuning parameter. So whenever you have some tuning parameter for which you need to know a good value, cross-validation is very helpful. What you do is simply this. You take the different possible choices for the tuning parameter value. Accordingly, you get different members of your family. You apply all of them using cross-validation. See for which particular value of the parameter you get the best cross-validation score. You pick that. Now, I just gave a brief overview of the two application areas. Now we are going to take a look at them using R, and then things will become clearer.